Okay, uh, so the plan today is to finish just a couple of little details from the material from last class, and then to go through a selection from chapter 11, conic sections. So we've already talked about parabolas actually that are a type of conic section, and today we're going to talk about circles, another type of conic section. We won't be covering ellipses or hyperbolas, and we won't be covering the parabola material in chapter 11, but as I mentioned before, this material on conics can be expanded or reduced. It's, flexible material, so we'll cover a little bit less just for time considerations. I did post the section 11.1 homework this morning, so after I figured out what I think we can get through today, I posted that so it's available, and that is the last homework set that will be posted. So all of the homework for the course is now available. Just a reminder that this week is the Unit 3 exam week on chapters 7 and 8. So that exam is due the 8th, this coming Sunday by 11:59 p.m. And again, I strongly recommend not waiting until the last day or two to take that exam. I'd probably recommend taking it this evening. And that way, if anything goes wrong, you have a full business day buffer to get anything worked out. The final exam is scheduled for kind of next week, but it's going to be available tomorrow
I have a
morning.
question when you get to.
Okay, just a sec. The final exam is
I emailed you.
okay, just a second. So the final exam is available. It will be available tomorrow, the 6th at 9 a.m. and it'll be due Friday the 13th. So just over a week from today at 11:59 p.m. And the same comment goes for the final exam. I would strongly recommend not waiting until Thursday or Friday to plan to take the exam. I strongly recommend planning to take it Wednesday at the latest. And then that way, if anything does go wrong, that gives you some buffer uh, to work through that exam. The material will be comprehensive, so it'll be chapters 1 through 9. We'll leave 11.1 off since that's kind of just the last little tail end of things here. But chapters 1 through 9, what we covered in class over those chapters, basically what was on unit 1 through 3 exams, which takes us up through chapter 8, plus the bit that we did in chapter 9. So that is the material for the final. And you should see the sample final exam posted later today, and then the actual final exam available tomorrow at 9 a.m. Okay, so I think somebody had a question.
Yeah, I emailed you. I've been trying all week to take the exam, and Examity won't let me do it. I don't know what to do at this point. Like I said, I tried to email you, and I've tried to take
Okay.
it all week.
Okay, yeah, if you would be able to either pop into office hours, I have office hours at noon today, from noon to 1:30, if that would work.
I know we
Um,
had this problem before. I have 6 classes. I
okay.
can't meet you, so I'll just figure it out.
Okay, or if you can send me like a screenshot or something, or or if there was another time that you could meet, yeah, okay. Um, any other questions on anything? All right. So let's jump into finishing up these last couple of problems in 9.5 and 9.6. So we're revisiting this problem from last time. Like I said last time, I kind of took a slightly wrong direction, and I think course correcting at that point would have been not the clearest way to go about addressing this. So I ended up just, cutting that little bit out of the lecture last time and revisiting it this lecture. I think that is the best way to go. So as kind of an aside, if you want a little bit of practice after we solve this problem today using the cleaner method, go back to the last lecture and, think through, okay, could we have made that work out? It wouldn't have been the prettiest path to make it work out, but could we have made it work out? And the answer is essentially yes. But it wouldn't have been as clear as this example. So the problem stem is that Sully is having a party, wants to fill a swimming pool. If he only uses his hose, it takes 2 hours more than if he only uses a neighbor's hose. If he uses both together, the pool fills in 5 hours. How long does it take for each hose to fill the pool in hours? And so we can draw out a grid where we have the information for just the neighbor's hose, for just Sully's hose, or for both together. And one way we can think about this is the rate that the hose fills the pool, which is where I kind of started last time. But the other way we could think about it, that's the cleaner way, is looking at the time that it takes to fill the pool, the more natural way, obviously, from the problem statement. And let's call the time to fill the pool with just the neighbor's hose, let's call that X. And if Sully uses only his hose, it takes 2 hours more than just with the neighbor's hose. So Sully's hose only takes X plus 2 hours to fill the pool. And if they use both hoses together, it takes 5 hours. So we can look at the proportion of the job completed per hour in each of these three situations. So with the neighbor's hose only, it takes X hours to fill the whole pool. So we fill 1/X proportion of the pool per hour. Sully takes X plus 2 hours to fill the pool. So his hose fills 1/X plus 2 proportion of the pool per hour. And the two together take 5 hours to fill the pool. Um, so together they fill 1/5 of the pool per hour. And these first two added together, the neighbor's hose plus Sully's hose, should equal the third one, the proportion per hour filled up with both hoses. So we have that 1/X plus 1/X plus 2 should equal 1/5. And we see we have a rational equation. As a little aside over here, we know that X cannot be 0 or -2. But kind of clearly those aren't realistic solutions to this problem anyway. We solve this by multiplying by an LCD, or here I'll just multiply by X times X plus 2. So I get X plus 2 plus X equals 1/5 times X plus 2. Or on the left side, I have 2X plus 2 equals 1/5 times X squared plus 2X. And I see that I end up with a quadratic equation I'm looking to solve. I think to make things a little easier, I'll multiply by 5 to get that off of the X squared term. So I have 10X plus 10 equals X squared plus 2X. And then I'll subtract everything over to the right side. And then I'll just kind of flip things around left to right. So I have X squared plus 2X minus 10X is minus 8X. And then my plus 10 comes over to the right as a minus 10 equals 0. And I now have a quadratic equation to solve. If I look at this for a few minutes, I'm going to see that it's not going to factor nicely. The factors of -10 look like something like 1 and 10 or 2 and 5, and neither of those combine nicely to make a -8. So I'll use quadratic formula here. So X equals -b, or negative of -8, which is 8, plus or minus the square root of b squared. -8 squared is 64. Minus 4 times a, 1, times c, -10. And all divided by 2a. So all divided by just 2 times 1 or 2. or I end up with 8 over 2 is 4, plus or minus. And let me look at this discriminant in here. So I have 64 minus a minus is a plus 40, or that's 104. And 104 is 4 times 26. So what's the square root of 104? That's the square root of 4 times 26, or it's 2 root 26. And these twos divide out. So I have x equals 4 plus root 26, or x equals 4 minus root 26. Now I know that root 26, well, square root of 25 would be 5, so square root of 26 is bigger than 5. So 4 minus a number bigger than 5, this is going to be less than 0. And remember, x is the amount of time it takes the neighbor's hose to fill the pool. So a negative answer, that's certainly not going to be the solution to the problem. So the neighbor's hose takes 4 plus square root of 26 hours, I guess, to fill the pool by itself. And then Sully's hose by itself takes x plus 2 hours. And if I just add 2 to this right-hand side, I get 6 plus square root of 26 for Sully's hose. And what did I get for that? About 9.1 hours for the neighbor's hose and about 11.1 hours for Sully. So that was our redo of this example. And again, if you look back at kind of how I approached it last time, I I just read a little more into the problem than was actually there, and that's one of the hazards of making of prepping the material before Thanksgiving break or whatever. I would prepped it, uh, and then it was a while since I had taken a look at it. So, but note that we don't know how big the pool is, and we don't know what the actual flow rate of their hoses is, right? The hoses might be like gigantic fire hoses and the pool might be enormous, or they might be little tiny hoses and the pool might be a little, toddler play pool kind of thing. So based on the information we have in the problem, we can't tell how much water was filled up in 5 hours in this case, or filled up per hour by Sully's hose. But we can find the times that it takes them to fill the pool with each of the hoses individually. Okay, so this was also a little bit of a review of rational expressions, rational equations, clearing fractions, and so on. And we saw this quadratic equation coming out at the end. All right, moving on to 9.6. Again, last time with 9.6, we covered quite a bit of the material. And one of the big ideas was that y equals x squared, the quadratic function, has this kind of U shape. So its graph looks like this, and in particular, a general quadratic function, like this, for instance, if I have y equals ax squared plus bx plus c, our U shape opens up if a is bigger than 0, and it opens down if a is less than 0. If our quadratic opens up if a is bigger than 0, the coefficient of x squared, then we have this important point down here, this minimum, and we call this the vertex. And we saw that the x coordinate was negative b over 2a, and that's the axis of symmetry that my graph of my quadratic function is symmetric about. So those were some of the geometric properties that we saw last time. Okay, let's look at this next example then. So for each of these following statements, determine whether it's true or false for quadratic functions that look like y equals f of x equals ax squared plus bx plus c, where a is non-zero. So is it true that every quadratic function has an axis of symmetry? Yeah, it is. This negative b over 2a, as long as a is not 0, I can compute what that is. It's just going to be some number, and x equals that number is going to be my axis of symmetry. So this axis is x equals negative b over 2a. Now b might be 0. That's perfectly okay. My axis of symmetry can be x equals 0, just the y-axis. There's nothing wrong with that. If a were 0, this would blow up. But again, we're not allowing a to be 0. So is it true that every quadratic has an axis of symmetry? Yes. Is it true that every quadratic function has at least one real root? Well, we saw algebraically already that no, this isn't true. But geometrically, just looking at the picture, does this make sense? We had looked at this with when looking at the discriminant earlier. But geometrically speaking, we can even see that this is clearly not the case. We might have a quadratic function like this that has, say, 2 real roots, so it has at least one real root. If we took this quadratic function and moved it up a little bit, we might be in a situation where we have only one real root. In other words, it's something like a perfect square. It has one repeated root. And if we keep moving it up from there, we have a situation where we have no real roots. So does every quadratic function have at least one real root? We can say no in 2 different ways. One, based on the discriminant. If the discriminant is positive or 0, we have at least one real root. But if the discriminant is negative, the thing under the square root sign in the quadratic formula, if that's negative, we have no real roots. We have 2 complex conjugate roots. Or we can look at this more geometrically and ask where are intersections with the x-axis. We could have 2 of them. We could have exactly 1, or we could have 0. And because of the existence of this case, there are some quadratic functions that do not have any real roots. And as an aside, we can make an association between the algebraic structure and the geometric structure. This is discriminant strictly bigger than 0, discriminant equals 0, and discriminant less than 0. That corresponds to those kind of 3 different geometric ideas. And then lastly, is it true that every quadratic function has a vertex? And yes, this is true. We can always take ax squared plus bx plus c, rewrite it as rewrite it in vertex form. And what did I do here? I effectively added b squared over 4. I would have an a squared down there, but there's an a out in front, so I just have an a. since I added that on in here, I'd better subtract it off so that net I don't add anything. And these are the X and Y coordinates of my vertex. Oh, where did I get a minus there? That should be a plus. These are my X and Y coordinates of my vertex. So negative, what did I call this? I think R and V last time or something like that. And V. Is there any reason that I can't compute any of these? Again, the only problem would be if, say, A was 0, but we're not allowing A to be 0. I mean, if A was 0, I don't really have a quadratic function anyway, I just have a line. So is it true that every quadratic function has a vertex? If I put it in vertex form, I can find R and V as long as A is not 0. Yes. And of course, any quadratic function, even something like this, still has a vertex, a minimum point. Or if it was opening downward, if my coefficient A was negative, it would have the vertex at the maximum point. So every quadratic function has a vertex, every quadratic function has an axis of symmetry, but not everyone has at least one real root. However, recall that if we do have one or two real roots, then they're symmetric about the axis of symmetry. So in the case that I do have, say, two real roots like this, here's my axis of symmetry, and my one root is as far to the right of the axis of symmetry as the other root is to the left. So we can really now think about quadratic functions kind of in the algebraic sense, using things like factoring and completing the square and quadratic formula and so on. Or we can think of them in the geometric sense, using these properties like vertices and which direction they're opening, whether it's up or down, and so on. And we can even often equate those two ideas through, for instance, our understanding of the algebraic side with the discriminant and the geometric side with whether we intersect the x-axis or not. Okay, let's try to graph this function, y equals x squared minus 4x plus 3, using the geometric properties of quadratics. So we're going to choose to write this in vertex form. And I want to complete the square here. So I would like this to end up being x minus 2 all squared. This would give me firsts, x times x is x squared. Outers is minus 2x, inners is minus 2x, so minus 4x. And then this would give me a plus 4 that I've added on. And then since I added on a plus 4, I need to subtract off 4 so that net I'm not adding on anything, right? I just added on 0 in a creative way as plus 4 minus 4. I grouped the plus 4 in with the quadratic and linear bits, and I grouped the minus 4 in with the constant bit. So x minus 2 squared minus 1. And I see I have a vertex at x equals 2, y equals negative 1. Right, when x equals 2, I get 2 minus 2 squared is 0. That's when y equals negative 1. And I see that my coefficient of x squared, or the coefficient in front of the x minus 2 squared, is positive, so we're opening up. So I have a vertex at 2 comma negative 1. I'm going to be opening up, so going this direction. And the other thing I can ask maybe is, what are my x-intercepts and what is my y-intercept? My y-intercept when x equals 0, oops, when x equals 0, y is going to be 3. So I go through that point. And if I want my x-intercepts, let me come off here to the right. We'll do a little bit of scratch work to get x-intercepts. My x-intercepts are when y is 0, or when x squared minus 4x plus 3 equals 0. And I see that this is going to be x minus 3 times x minus 1 equals 0, or x equals 1 or 3. So at x equals 1, or at x equals 3, 1 unit to the left and 1 unit to the right of my axis of symmetry. Here is my axis of symmetry with my vertex at the bottom there. Those are going to be my two roots. And it looks like my quadratic looks something like this. So I didn't have to plot kind of a whole bunch of random points. I plotted a couple of important anchor points just to just to help out with the graphing a little bit, but I didn't have to plot, 6 or 8 or something kind of random points. I was able to use a lot of the information about the geometry and the vertex and so on to get an overall idea of what my picture is going to look like. And then I got a couple anchor points, my vertex, my two x-intercepts, my y-intercept. It's really, never a bad idea to get a y-intercept. It's usually really easy to get. The x-intercepts might be easier to get, harder to get. These ones weren't bad. But in another context, maybe it's not, maybe it's more of a hassle to get the x-intercepts. Okay, and then for our last example, suppose that a ball is thrown into the air and the height at time t is modeled by h of t equals negative 16t squared plus 24t plus 40. So this would be like if somebody is standing on a platform that is, say, 40 feet high, and they throw a ball into the air with an upward velocity of 24, say, feet per second. And maybe I should, that actually kind of gives the impression that the parabola is kind of the motion of the ball, but it's really, they're throwing the ball up, it's going up, and then it's coming straight back down and landing at height 0. So the question is, if I throw the ball straight up in the air, it's going to go up, stop, come back down. It's going to reach a maximum height. What is that maximum height? So let's take a look at negative 16t squared plus 24t plus 40. If I factor a negative 16 out of the first two terms here, okay, I know that 24 over 16 is 3/2. It's 8 times 2 on the bottom and 8 times 3 on the top. If I want to make a perfect square, I need t minus 3/4 squared. These firsts will give me t squared. The outers will give me minus 3/4 t. The inners will give me another minus 3/4 t to make minus 3/2 t. And then my lasts I'll be adding 3/4 squared times -16. That's what I've added on here. So I've got to subtract that off over here. Or I see I can write h of t as -16 times t minus 3/2 all squared plus, and this is going to be 40 minus is a plus. It's going to be 16 times 9/16. Or h of t is -16 t minus 3/2 squared plus 49. And I see that my vertex has y coordinate 49. So h of t is going to, what, at time 0, we're at height 40. It's going to go up to 49 at time 3/2, and then come back down. Right. I know this is a quadratic opening down because the coefficient of a is negative. So this vertex is going to be a maximum. And my maximum height is going to be the y coordinate of that vertex, 49. So what's the maximum height reached by the ball? 49 feet. So throwing upwards at an initial speed of 24 feet per second, the ball will go up another 9 feet, reaching a final height of 49 feet, 40 from the platform it started on, another 9 from the initial velocity, before it starts coming back down. Any questions on that? Okay, so that finishes up chapter 9, and the plan now is to switch gears a little bit into chapter 11, talking about conic sections. And I'll leave the discussion about why these are called conic sections. It might seem strange to be referencing a cone when we're talking about things like parabolas and circles uh, that seem very kind of bendy, and we think of cones as kind of, uh, more kind of straight line figures. But in short, it has to do with the idea that if we draw a cone like this, and we take slices of this cone, if we take, say, a plane and slice the cone this direction, the image of that cone on the plane looks like a parabola. If I take the cone and slice it in this direction, oh, I don't know why OneNote thought that I wanted a triangle there, but the image of that cone on the plane looks like a circle. So that's why, for instance, parabolas and circles are called conic sections. We also have hyperbolas and ellipses, which we're not going to get into in this course. Okay, so we have a definition for a circle. A circle is the set of all points x, y, all two-dimensional points, that are a fixed distance r from a given point h comma k. R is called the radius of the circle, and h comma k, that point, is called the center of the circle. So importantly, h comma k is not, that point is not on the circle, it's the center. Then we go distance r away from that in all directions, and that's what traces out the circle. As we'll see, interestingly, a circle is actually a relation between x and y, but it's not a function. Why is that? Well, let's consider the geometry for just a minute here. Here we have h, k, that's my center point. That's not a point on the circle. And then I have a distance r, And the points on the circle are all the points that are distance r away from that point h comma k. Well, I see immediately that I failed the vertical line test in most cases, right? I could go r units away in this direction or in this direction and have two points that are on the circle that have the same x value but different y values. So the circle is not a function, but there are some things we can do to make it behave a little bit like a function. We can maybe talk about the top half of a circle or the bottom half of a circle, and each of those individually are functions. So there are some ways to kind of work around this issue. Um, we're not going to really get into those in this course, though. But the circle in and of itself is not actually a function. Now, one challenge is we're talking about the distance from a given point. Well, we need to know how to compute distance in the first place. So let's take a look at that. Let's try to find the distance between these 2 points, 2 comma 0 and 5 comma 4. So 2 comma 0 is this point. And 5 comma 4 is that point. And I want to know the distance between the 2 points, or in other words, the length of this line segment. I'm going to call this D. Now, something I realized is if I had 2 points that were, say, horizontally adjacent, if this were, say, 2 comma 3 and 5 comma 3, then the distance is just 5 minus 2, or say 3 units. So if I have 2 points that are horizontally adjacent, or horizontally, adjacent, distance is easy. If they're vertically adjacent, distance is easy. It's just the difference between the x components or the y components. When we have a line that's kind of slanted, when we deviate in both the horizontal and vertical direction, things are a little bit more complicated. But what I can do is I can break down this line going from 2, 0 to 5, 4 in this kind of diagonal direction. I can break it into a horizontal component and a vertical component. And hey, nicely enough, this is a right triangle. And this kind of third anchor point here is going to be at x coordinate 5 and y coordinate 0. So it kind of shares one of the coordinates from one of the points and one of the coordinates from the other point. As an aside, I could also have drawn this triangle this way, and it would have used the x and y coordinates that are just the opposite. It would have been at 2 comma 4. But I chose to draw it this way, so we're using 5 comma 0 as the other third point. Well, I noticed that this blue line distance, the length of that blue line is, well, what is it? It's just the difference in the x coordinate values. It's 5 minus 2. And I noticed that this green distance here, the length of this green line, is the difference in the y coordinate values. It's 4 minus 0. Or what I end up with is, if I kind of pull this figure off to the side, I have the distance that I want. I have my horizontal deviation between the 2 points, my vertical deviation between the 2 points in a right triangle. And maybe I'll call this, say, x1 minus x0 or something like that, just the difference in the x coordinates between the 2 points 2, 0, and 5, 4. And maybe I'll call this one, say, y1 minus y0. Well, I see that I can apply the Pythagorean theorem. I have that d squared is x1 minus x0 squared plus y1 minus y0 squared, or my distance. Maybe I should be drawing this in black because distance is black over here, but my distance is the square root. We don't have to worry about the negative square root because distances are always positive, so or non-negative, I suppose I should say. So we're just taking the positive square root. I take the horizontal deviation, the difference between the x's, and square it, and the same for the y's. Note that because these are getting squared, the deviations, the y1 minus y0 is getting squared and the x1 minus x0 is getting squared. It doesn't much matter which one we pick to be first or second, because if we ended up with a negative, it's going to get squared off anyway. Or coming back up to our problem, 5 minus 2 is 3 is my horizontal deviation. 4 minus 0 is 4, my vertical deviation. Well, this looks like a 3, 4, 5 triangle. So in this case, the distance would be 5. We can see that by it being a 3, 4, 5 right triangle, kind of a recognizable structure. Or we might see that by using the algebraic definition. D equals the square root of, well, what is it? X1 minus x0. So we'll take, say, 5 minus 2 squared plus y1 minus y0, 4 minus 0 squared. Or algebraically, we see that this is the square root of 3 squared plus 4 squared. Square root of 25 is 5. So this formula, this distance formula, is the distance between 2 points, x0, y0, and x1, y1. And again, it doesn't matter how we label the points. Because if I chose y1 minus y0, or if I chose y0 minus y1, the only difference between those is a factor of -1, and that gets squared off anyway. So if I chose, this point is 0 and that point is 0.1, and you chose the opposite, we get the exact same answer in the end. In some sense, we're kind of like square rooting a square. So in some sense, we're basically taking like an absolute value anyway, right? So we're not really worrying about order, we're worrying about distance between the two. Okay, so what about this example? Find the distance between these 2 points. Obviously, we don't have to go through all of this work every time. Now that we've generalized away from these details, we can just use the formula. The distance is the square root of the difference in the x's, say -1 minus -3 squared, plus the difference in the y's, -2 minus 4 squared. And again, if you picked -3, 4 as your 0 point, or whatever as your 1 point, your first one, and you pick -1, -2 as the one that comes second, you'd get exactly the same answer. We do have to be careful with our negative signs here. -1 plus 3 is +1. +2. Where did I get? -1 plus 3, +2. And -2 minus 4 is -6. Or this is the square root of 4 plus 36. It is the square root of 40. Or maybe I write that as 2 square root of 10. That's probably about the best that I can do. So now that I have a distance formula, I can find the distance between 2 points pretty quickly. Another important idea related to distance and circles and so on is the idea of a midpoint. So let's try to find the midpoint of a line segment. If I have a line segment whose endpoints are -1, -2, and -3, 4, so I have this line segment, I would like to find its midpoint, right? So that if I was walking from one end to the other, I see what distance that is. And then I say, okay, if I started walking from one end and went half that distance, what point would I be at? Right? What is the midpoint? This seems like a complicated problem. Like I have to figure out the distance, figure out half the distance, point myself in that direction, go that distance. It seems like it's going to be a lot of work. But actually, I might realize that the midpoint along this line, well, when I traverse the line, I'm going a certain horizontal distance and I'm going a certain vertical distance. Well, the midpoint is just when I go half that horizontal distance and half that vertical distance. I mean, I can really see this if I think of this in terms of, say, maybe similar triangles. Right? These two triangles are similar triangles. And I can see that one is just half the size of the other. So if I have x naught, y naught, and x1, y1, the midpoint just has x coordinate that's the average of the x's, and y coordinate that's the average of the y's. We're just halfway between the horizontal extremes and halfway between the vertical extremes. That's our midpoint. So initially this looked like a really complicated problem. I have to point myself in the right direction and go the right distance and all of that. I could think of it that way, but it's easier to think of it this way. So for these points, what is my midpoint? Well, the x coordinate is going to be the average of the x's, -1 plus -3/2, and the y coordinate, the average of the y's, -2 plus 4/2. Or my midpoint is going to be, for the x coordinate, -4/2 is -2. -2 plus 4 is +2/2 or 1. So midpoint at -2, 1. And that looks about right from the figure that I drew over here. Of course, that's just a rough figure, so it's maybe a little bit off, but it looks like it's in the right ballpark. Okay, so moving on to the next example then, write the standard form of the equation of a circle with center 2, -3 and containing point 2, 5. Well, let's first take a look at the equation of a circle. Well, we have a kind of geometric description of a circle, set of all points that are a fixed distance from a center. Well, how does that translate to an algebraic equation? Let me actually copy this definition down here. I was going to just append this as a note, but if I start hitting enter up there, it's going to throw off all of my spacing for everything else. So here's my definition of a circle. So what is the distance between 2 points, x, y, and hk? Well, the distance between those is x minus h, the horizontal deviation squared, plus y minus k, the vertical deviation squared, and I take the square root of that. That's the distance between a point on the circle and the given center point that sets that center of the circle. And this distance should be a fixed number, r. Or by squaring both sides, I see I have x minus h squared plus y minus k squared equals r squared. This is my standard form of my circle in the algebraic side of things. So I have a way to think about a circle geometrically, and I have kind of an equivalent way to think about a circle algebraically. So if I'm looking for the standard form of the equation of the circle with center 2 comma negative 3, I know that this is h comma k from above and containing the point 2 comma 5. So this is going to be a point x comma y that's on the circle. If I know three things, if I know h, if I know k, if I know the x and y coordinate of the center, and if I also know r, the radius of the circle, I've uniquely defined that circle. I know two of those things right off the bat. I'm told what the center is, so that tells me h comma k. I have one additional criterion that this point 2 comma 5 has to be on the circle. So the distance from 2, 5 to 2, negative 3 has to be the radius. I could do this a couple of different ways, but one way is just to plug everything into the equation of a circle. So 2 minus h, so x minus h squared plus y minus k, 5 minus a negative 3 squared equals r squared. I don't know what r is yet, but this equation will tell me. Nicely enough, this is 0. These are horizontally adjacent points. So 5 minus a negative 3 is 8. So I have 8 squared equals r squared. R has to be positive 8. Note from the definition that r is a distance. This implies that r is bigger than or equal to 0. So we wouldn't say the radius is negative 8. I guess it like kind of in a sense doesn't mess things up too much if you were to say that, but it's just kind of an awkward way to think of a radius. So we take the radius to be positive 8. Or I have x minus h, what is h? 2, squared plus y minus k, what is k? Negative 3. Y minus negative 3 is y plus 3 squared equals r squared, or 64. Okay, a little more straightforward one. Graph the circle with radius 3 and center 2 comma negative 4. So again, remember we took our geometric idea, translated it into an algebraic equation, and we know that this is the general format for a circle. X minus h squared plus y minus k squared, where hk is the center, equals r squared, where r is the radius. Well, here I just have to plug in. Let me zoom out a little bit so I can get this all on the screen here. So I see my center 2 comma negative 4. So I have x minus 2 squared plus y minus a negative 4, y plus 4 squared equals r squared, equals 3 squared, or 9. Okay. That's my equation of the circle. And I suppose I could maybe pick some different values for x and find associated values for y and vice versa. I could maybe do that, but my goal here is to just get a graph of the circle. If I'm looking to graph the circle, it's probably a little more natural to just use the geometric description. So if I have a center at 2, comma, -4. Maybe I'll draw that in, say, blue here, because it's not actually part of the circle. It's just the center that sets the position of the circle. And if I have radius 3, so here is 2, -4. What I'm typically going to do is just look at horizontal and vertical deviations to start with. So radius 3 means I'm going to go to the right 3 units. That will be a point on the circle. If I go to the right 3 units from the center. If I go to the left 3 units from the center, that will be a point on the circle. If I go up 3 units, that'll be a point on the circle. And if I go down 3 units from the center, that'll also be a point. I have 4 points on the circle. I can pretty well draw the circle now. And I mean, I'm not the best artist in the world, but that's more or less what our circle is going to look like. Has center at 2, -4, and this radius of 3 units in, say, that direction or in that direction, but also really in any of these directions. Any questions so far? Okay, and we have one last example. We want to rewrite the equation of a circle in standard form to get it in this algebraic form so that we can then find the center and the radius and then use its geometric properties to graph it. We might run out of time here, but if we go a minute or two over, you can feel free to come back and just watch the recording. I noticed that I'm not in standard form because I have some x squared and x terms that aren't all under a single x minus h squared, and similarly with y. But nicely enough, I know how to handle this. Oops, x squared minus 12x plus y squared minus 6y. And I'll say equals -42. I'll put that constant on the other side. I want this to be x minus h squared. All I need to do is complete the square. This is going to be x minus 6 all squared, right? So then my first give me x squared, my outers give me minus 6x, my inners give me minus 6x, that's minus 12x. Then my lasts, by putting this under a perfect square like this, I've effectively added 36 to the left-hand side. I better add 36 to the right-hand side as well. And then I do the same for my y. Y minus 3 squared. Right, just completing the square here as well. My first give me y squared. My outsides give me minus 3y. Inside's another minus 3y for minus 6y. And my lasts plus 9. So I've effectively added 9 to make the perfect square for the y's. So I have to add 9 here to the other side as well. Or I have x minus 6, whoops, 6 squared plus y minus 3 squared equals, well, 36 plus 9 is 45. Minus 42 is 3, or that's square root of 3 squared. I have a center of 6, 3, and radius of square root of 3, or something that's maybe about 1.8 or so, something around there. And I can use this center and this radius to make a graph of this circle. So there is 6, 3, and going, let's say, roughly 2 units in any direction. So a little less than 2 units up, a little less than 2 units down, same to the right and to the left. And my circle should look about like that. And just to be clear, these are the points that are on the circle. This center point here, I didn't take the time to change the color, but that center point is not actually a point on the circle. It's just helping me to set the position of the circle. Okay, so that wraps up our material for today and our material for the whole course. Remember the Unit 3 exam this week, as well as the final exam coming up in the next day or so and going through next week. So just make sure you don't wait until the last minute to take either of those exams. As always, you can feel free to reach out to me anytime this week or next week. I don't have regularly scheduled office hours during final exam week, so from Tuesday on. But if you have a question or something, I'm more than happy to answer, or if you want to meet over Zoom, I'm more than happy to do that. So I hope the semester has been a good semester for you. I hope final exams and projects and all of that go well, and enjoy the holiday break. So have a good one.